Hello and welcome to another video. In this video we're going to be going over the problems from the weekly contest 402, and let's get started. So in this first one, you're given an integer hours representing the time in hours. Return an integer denoting the number of pairs where the pair form a complete day. A complete day is a time duration such that is an exact multiple of 24. For example, 1 day is 24 hours, 2 days 48, and so on and so on. So in this first example, this is a pair because 12 and 12 is 24, and then 24 and 24 is 24. And in the second example, it's these two, and then it's also these two, and then it's also these two. So what we can do is, instead of keeping track of multiples of 24, like really what we're asked is like, give all combinations of numbers that add up to 24, and then we can take our number if it's bigger than 24 and just mod it by 24. So for example, if we have 48 hours, we can mod by 24 and we'll get 0, and so on and so on and so on. And that'll kind of bucket everything in the right thing. So like, we don't really need to store any number more than 24. And then basically all we need to do then is for every single hour that we run into, we just check what's the count of the other one we need. So for example, for 12, we'll just say like, okay, we're at 12. What do we need for 12 to get to 24? We can just do 24 minus 12. And then we say like, okay, so how many counts of 12 do we have? And then for that number, we can basically combine it with every single 12 beforehand. So what it'll look like is you're going to have a dictionary. So you're going to go through this first number. 12 will have a count of 1, and there is no complement. Then for this one, you're going to say, okay, we're looking for a 12. How many 12s do we have? We have 1. So then the result will be 1. And now we have two 12s. Then for 30, we're going to modify by 24, so we'll get 6. So we need an 18. Do we have any? No. So we'll store it in here. 24, we'll just go to 0. So we need another 24, which is another 0. We don't have any, so we'll just store it. And then for this 24, we'll say, okay, we're looking for a 0. We have one of them, so then we have 2. So that's kind of the idea, and in the code, it's pretty easy. So you just create a dictionary, and it's basically like a running two-sum. So for every hour in the hours, you mod it by 24. You look for what complement do I need, and then you just, however many you have, you add it to your result. And then you store it in your hash map. So pretty standard problem. The second one, same kind of thing. So 72 will reduce to 0 because 72 is just 24 by 3. So we say how many zeros do we have? 0. So we'll just store 1. 48 will be a, will get reduced to 0. How many zeros do we have? 1. So that's one pair. And then we have 2 zeros now. And then 24 will reduce to 0. And how many pairs do we have? We have 2 zeros, so that'll be 2 more. And we have 3. Store that, and then 3 will reduce to 3, and we'll have 3, 1. So that's kind of the problem, and this solves. I guess you can kind of like, I guess for the easy problem, you can brute force all pairs, and that would probably be the easy solution. But I just did this for both because it's pretty easy. Like, this is not super complicated. So this works for this guy, and it works for this guy. Same exact thing. Basically, just a two-sum with more things to look for than just one. Okay. And yeah, anytime you're asked for a number of pairs, and there's kind of two ways to do it. You can either get a count beforehand and then get all the pairs, and then that would give you duplicates, because you'd get for every pair, like let's say A and B is a pair, you'll get the pair A, B, and B, A, unless you have some condition. Or you can just say for everything, let me just compute everything before then, and then that will give you no duplicates. So you can either do duplicates, divide by 2, or just for every number, compute how many you can make with that number, and that would give you no duplicates. Either one's fine. Okay. Then let's look at the third one. And yeah, the second one, I mean, I guess they don't really have like runtimes yet for all these, so yeah. Interesting, this analyze complexity, how it's working here. Okay, linear, cool. Yes, yeah, you can be kind of like, I'm interested, I'll try this out for like more complicated stuff and see what complexity we get like for the last problem. So for this one, this one's also pretty easy. You're given an array power where each element represents the damage of a spell. Multiple spells can have the same damage, and if you pick a spell with damage power, you can't pick a spell within 2 of that power. So for example here, if you pick a spell with power 3, you can't use 1, you can't use 2, you can't use 4, you can't use 5. And for each one of these spells, you can use it one time, but if you have a duplicate, you can use it multiple times. So we can use like 1 and then 1 again. So in this first example, you would use 1, then you would use 1. You can't use 2, you can't use 3, but you can use 4. So you'd use 1 on 4, you get a power 6. In the second example, you can use the 1, and then you would use a 6 and then the 6. And this is basically just a pretty standard DP problem. So for every number, so first of all, we want to get rid of duplicates. So to get rid of duplicates, pretty easy. For every number, you just have the, we can just store the count and then we can sort those. Right, so essentially instead of this kind of thing, we'd have like 1 with a 1, 6 with a 2, 7 with a 1. Then we can just go through the keys, and then it's a take or not take, pretty much. So if we take, then the number of like the spell power we have is the power of the spell times the count of the spell. And that's this thing right here. And then if we take, so for example, if we take a 1, the next number we go to can't be 2 or 3. So we have these spells in an array. So if we have spells like 1, 2, 3, 4, 5, let's say. And if we take a 1, we just say, we can't go to 2, we can't go to 3, let's go to the next one. So I'm just manually checking to make sure the next index is not 2 or 3, and then go to the next one. So if it was like 1, 4, then you could do it. And so that's basically a take. So if you take, then just go to the next index that isn't within 2 of your current one, and you just do a loop of looping 2 or 3 times, which is fine. It's still that's still a constant operation. And if you don't take, you just go to the next number and you try to take it or not. So pretty easy take or not take DP, building problems like this, and pretty straightforward. You can do this bottom up to get rid of the space complexity, because for every spell you only need to move maximum 3 forward, right? So if we have this, if we take this, then this is like a house robber, except for like basically if you rob here, you can't rob 2 houses that are next to it. So you would go here and then from here. And so you can just store like a couple. So all you need is to store like 3 or 4 numbers, because every number relies on the previous 2 and the next 2 and so on. So you can just store a couple numbers and get that down to 1 space if you want to. And that works as well. I think you'd use like a deck or something for that. Yeah, so you could do that if you want to. I just did this. But yeah, so the last one is going to be the tricky one. So here we have a peak and a peak. There's a lot of like peak problems. So a peak just means you have a number that's greater than its previous and next element in an array. You're given an integer nums, or integer nums and queries, and you have 2 types of queries. You can either get the number of peaks in a range, or you can modify a number and return the answer of this thing. So when you read this is basically almost the same. In fact, it is the same as, let's say a peak is a 1 and a non-peak is a 0. So we just have like peak, non-peak, maybe, something like this, right? 1, 0, 1. So let's say something like this, who knows? You can't have 2 peaks next to each other, so let's say something like this. And so basically you're asked like, okay, if I have this, how many peaks do I have in some range? So let's say this range. So you can do this with a prefix sum, right? Like if that was the only problem, just like give me a range, or I'll give you a range and give me the number of peaks in a range. You can do that with prefix sum. But then the problem is you're modifying a number afterwards, and I'll kind of show how that works. So your peaks can change. So when you modify a number, some peaks can change, and then you have to do a range sum query again. And for a prefix sum, anytime you modify a number, you have to do the entire prefix sum. But let's say the problem was just given a bunch of 1s and 0s. You can modify 1s to 0s and 0s to 1s. Let's say I modify here. So you need a data structure that can modify and can give you a range sum query. And so for that, you can use a segment tree, and I have a video on segment trees. So it definitely should be, to do this problem, I would recommend be familiar with segment trees. I'll link that one as well. But basically what a segment tree does is it lets you modify a number in log time, and it lets you query a range in log time, because it's like a tree. And the basic idea of a segment tree is all of these nodes represent a range. So maybe this is like 0 to the length of the array or something. And then all of these are like broken down. So maybe this is like 0 to 5, 0 to 10, or 5 to 10, and so on. And then the very bottom node of each tree is just the actual, like a range of 1. So maybe like 0 to 0, 1 to 1, and so on. I'm missing a bunch of nodes, but essentially that's what it is. And to update a number, you just have to go down a path. So you would just go down some path, modify, and then go back up the path. So that's why it's log time update. And to query, it's also log time, because you just like go to the right place to get your query. So you might go down like a couple branches, but essentially it's log time. And yeah, like I said, in my segment tree video, I have that. So now basically all we need to figure out is, let's say we have an array of numbers and an array of peaks, how to make the modifications and all that stuff. And let's look at the examples for that. So here, the first query, so query number 2 changes the value and query number 1 queries. So basically query number 2 does an update on your tree, and then query number 1 does a query on your tree. So here you want to change index 3 to 4, so you would change this to 4. And then the second one queries your whole tree. And here there are no peaks anymore. Once you change this, there's nothing. So this should return 0. And here you want to change index 2 to 4. It's already a 4. Then you want to query 0 to 2. So the other thing is they kind of show you here. Whenever you do a query, a number might be a peak. Like this is actually a peak if you look at the whole array. This is a peak. But when you do this query here, a number can't be a peak if it's on the outside of the query that you're doing. So like left, right is 0 to 2. So this can't be a peak because technically there is no number to the right of it, even though there is a number to the right of in the main array. So that's pretty easily handled, and I'll show you how. And then the third one is 0 to 4. So this is just this guy, and then you do have 1 peak. So let's figure out what happens when we change a number. First of all, let's figure out how to initialize a segment tree, what happens when we change a number, and like that's pretty much the problem. So let's go through this example here. Let's get rid of this thing, and let's just go through example 2. What happens when we change a number? What do we initialize peaks to? All that stuff. Okay, so here we have nums. So we have like 4, 1, 4, 2, and 5. So we can make another array for our peaks, and they'll be basically 1s and 0s. You can use Boolean values if you want. I just used, so maybe Boolean values would be faster, but whatever. So basically you just go through all your numbers and you check if it's a peak. So the rightmost and leftmost number can never be a peak because there's nothing to the left and to the right. So these are not peak, and we'll say 1 is a peak. So the only peak is this. So this will be 1, and these will be 0s. And then we can basically make a segment tree using this array. So this will be our array. And then we can query it. We can query it as well. Now, step 2, what happens when we change a number? So let's say we change this number. So if we change this number to, let's say, a 1, all we have to do is check, is this number still a peak? And are these two numbers still a peak? Because when you change one number, the number to the left and to the right might be a peak when it wasn't, and this number might change. So all you have to do is check 3 numbers. Did they become a peak? Did they switch? And then in here, like if they changed in the peaks array, then you make an update in your segment tree. So for example, let's say we had let's say we had this. So right now there would be no peaks if this was the case. But if I change this guy to a 1, now this becomes a peak. So you see how, like, if I change my number, the number to the left can become a peak and the number to the right can become a peak. And I can also have an example here, you know, if it's like this. Now there are no peaks, but if I change this guy to a 0, now this becomes a peak and this becomes a peak. So basically what you do is, let's say we have this example. When you change your number, you just check, is this number a peak now or not? It's not. And it wasn't, so you don't have to make an update. Now, is the number to the left a peak or not? It is, and it wasn't. So you do have to make an update in your tree here. So you would just update the tree at this node. And is this number a peak? Yes, and it wasn't. So you have to update the tree at this node. So that's the process of updating a number. You just update a number in your numbers array. And then you check, is it a peak or not? And did that change from what it previously was? You don't even have to check, honestly. You can just always call an update, but it's more efficient to like if it wasn't a peak and it's still not a peak, then you don't have to update your tree, because your tree will give you these queries, right? Now the second part, how do we get a query in the tree? And if we do a query like this, let's say we do a query from 2 to 4. So this, from 2 to 4, it's 404. Now notice that these two were peaks, but because we're querying like this, the number on the left side of the array and the right side of the array can't be a peak. So it's a pretty easy modification if we want to query from 2 to 4. Instead of querying 2 to 4, we know that the left and right most number can't be a peak. Instead, we can just query from the number right above the left. So we can query this. We can query left plus 1 and right minus 1 instead. So if we're asked to query this, instead we just query this guy. Because we don't need these two numbers. First of all, they'll be inaccurate, like they'll be ones in our tree, but like these will always be 0 in the result. So that's how you handle the second part. When you're asked to get left to right, instead of getting left to right, you get this instead. Because the left and rightmost number might be a 1, but there'll be a 0 in the result. So that's the basic modification. So if we're asked to query 2 to 4, instead we'll query 3 to 3. If we're asked to query 1 to 5, we'll query 2 to 4, and so on. Because like I said, 1 to 5, 1 might be a peak, but it's not going to be a peak in the result. So you know these two will never be a peak in the result, so you don't need to query those. You're just going to query everything other than the left and right bound. And then the rest of it is pretty straightforward. You just do your queries in your segment tree, and you do your updates. So let's look at the code there. Okay, and let's move it over here. So I copied this code from my segment tree video, and so yeah. So this is like some segment tree code that I changed a little bit. And there's two ways to make a segment tree. You can make it with an array, which I probably should learn to do eventually. I think it's more efficient, or with an actual tree. And so I use a tree. So a segment tree has a node, it has a value, it has a left child and a right child, and it has the left and right bound for the range it represents. So for example, if the tree is like 0 to 5, that means it represents the range in the array 0 to 5. Then you have your initializer for the, I'm not going to go too much in detail because I can link that video. You have your initializer for the tree, where that takes a numbers array, which will just be these peaks here, initialized right after we calculate them. And then we build the tree. Oh yeah, and also by the way, so this nums array, these two will always be 0, and then you just check for the rest of them, like are they a peak? Because these two can't be a peak because you have to have a number to the left and to the right. Okay, and so you just build your tree, and you just keep splitting your range in half until you get to a root node, and then you have an update, which same kind of thing. You keep splitting the range in half until you get to root node, recurse back up, and this is basically a sum segment tree where a peak is a 1 and a non-peak is a 0. And then here's the query. It's all the same kind of stuff. And I have these cases in detail in that video that I'll link. So let's take a look at the rest of it. And you can probably make this a little bit shorter, but this is what I did. So you make your peaks array. You go through all your numbers, and you just check, like, if it's a peak, let's update the peaks. Then you make a segment tree using the peaks array. Then you go through all the queries. And if it's a 1 query and the you make sure the range is valid. So for example, if I'm trying to get the range, like let's say left is 2 and right is 2, because like I said, we're not actually going to query 2 and 2, we're going to query left plus 1 and right minus 1. This would end up being 3 and 1, and this is like an invalid range. So I just check, is that range actually valid? Like, is the left actually less than or equal to the right? If it is, let's query that guy. If it's not, let's just do 0 because there will be no peaks. Otherwise, we have the update. And so for the update, first we update our number. Then we check so let's say we update this guy. Let's say we update this guy. We check, can this guy even be a peak? Like, does this guy even have, like, is this out of bounds? And if it's not out of bounds, is this out of bounds? Because in order for a number to be a peak, it has to have a left and a right that aren't out of bounds. So if that guy can be a peak, then we just see, is it a peak? And we compare it to its previous result. And if the result changed, then we call an update and we change it in the peaks array as well, because that's a 1. Same thing for our current number. If it is a peak and it wasn't, or if it wasn't, it is now, call an update, change it in the peaks array. And for the one after, same kind of thing, all that same kind of stuff. Then we just return the result. Yeah. And so a lot of code, but most of it is just the boilerplate for the segment tree. So like 65 lines is the boilerplate. This can probably be shortened as well, but yeah. So it's it's definitely on the easy side of the segment tree problems. Like, once you learn how a segment tree works, it's definitely pretty doable to be like, okay, well, if a number changes, there's only a couple peaks that change. I can just like check for those, and if they change, I can update my segment tree and I can get my range sum pretty quickly. So we can submit this guy, and you'll see that. So it is a little slow. I think maybe the array one might work better, or you can make like some other optimizations. I'm curious in this one. Huh, interesting. Okay, so it doesn't. Okay. Yeah, that is interesting. I'm going to try this with like graph problems and things. This is the same thing. Okay. So let's just do this by hand. Okay, so time. So for a segment tree, like I said, an update is log n and a query is log n. So for every number in the query, first of all, we have to like make the array. So that's O(n). Yeah, so that's already O(n) to just like make the peaks array and go through all that stuff. Then for every query, to get an answer, that's log n. So this is like q log n, and then to update is also log n, and you might have up to 3 updates, but that's still log n. Yeah, so I think it's something like this, where for every query it's a log n update or query, and space. So to make the segment tree is O of n, because you basically just have n nodes. Well, you don't have n nodes, you have n times 2 nodes technically, because your bottom level is n, and then it's like n over 2, n over 4, and whatever, which rounds to n over 2. So space will be n. Let's see if we have anything else. So peaks is O of n as well. Segment tree is O of n. Result doesn't count. So yeah, I think it's just like this for this guy. Let's see what it said for the other stuff. Kind of curious. So if we run this and we do this, let's see what we get. I mean, I guess this wouldn't be too hard to do because, yes, this is incorrect. This wouldn't be too hard to do because you can basically, this can basically just like, you can just ChatGPT, like you can put this into ChatGPT and tell it to give you complexity. So this is actually not, obviously it's not 2 to the n. It's, yeah, it's like 2 times n because we have a cache. So if we didn't have a cache, it would be 2 to the n because then we ever take or not take with no recursion. Yeah, so that one's wrong. Okay, but anyway, so to go through all the powers is O of n. To sort the keys is n log n. And then to do the DP is O of n. So this is n log n. And yeah, the reason I think I mentioned the reason you want to sort the keys is because this thing, you can't take things that are less than, like, you can't take things that are 2 less in either direction. So the easiest way to solve that is just go from the smaller one to the bigger one, and then you never have to worry about not taking something to the left, because if you have something like this, so basically what it's saying is like if you took 5, you couldn't take 3, but if you take 3, you're just not gonna even ever go to 5, so you'll avoid that case. So if you take 3, you'll skip 5. If you don't take 3, then you can go to 5, and that's fine. And if you like maybe take 4, you know, like you basically just like, if you take the one before, you'll never go to that one, so it kind of handles the previous and the next case for you if you sort. And space is linear. Yeah, I mean, like actually, so this would be O of 1, but it actually doesn't matter. This DP would be O of 1, but this is still actually this is still O of n. So like this DP would still be O of n regardless, like even if you space optimize, because we still have this stuff. Okay, yeah, so that one's good. Kind of interesting. Let's see that one was inaccurate. Let's check this one. It's accurate. All right, so linear and linear. Oh yeah, I didn't see the this guy. Let me run it one more time for the space. I want to see how accurate that one is. Linear. Okay, so that is accurate. Okay, hit or miss, I guess. All right. So here, pretty easy to see that it's linear and linear. And the easy problem is the exact same code. So linear and linear as well. And yeah, I think the AI thing was accurate on that one. Yeah, it's gonna be all for this one. And I think what I might do, and you guys can let me know what you think about this, is for this contest, usually at least the easy and probably this one are kind of easy. So I might just do the last 2 problems in more detail in separate videos instead of this whole contest in one, because I do feel like doing like the first and the first couple problems is kind of a waste of time. Also, if you're like on the level where you're doing these problems and struggling, then you should probably be doing like the daily problems anyway. But let me know what you think, if you like this format of all the videos in one, or just rather do like the hardest or maybe like the 2 hardest problems from a contest or something. So let me know what you think about that, and yeah, I'll see you next one. Thanks for watching.